hit this button, and we can start. So we're starting today with a limit of a sequence. This is something we did a few classes ago, and you have a homework problem that is due tonight with exactly these kinds of limits. In fact, I think I took this exact problem from your homework due tonight. So it should be something you can do. We know how to do the limit of sequences. We did a few of them before, and we talked about how you can combine to get more complicated ones. So let's see what people said for this one. 5 minus n to the minus 2 cubed. So 77 people answered. And the answers are completely split. It's like a 5-way race here for first. 14 people think it's minus infinity. 20 people think it's plus infinity. 23 people think it does not exist. And 15 people think it's none of the above. So split almost 4 ways perfectly. Let me give you guys a revote. So we're going to do this one. This is one you should be able to do. It's on your homework tonight. So you can't leave the class without knowing how to do this one. So let me give you another chance to revote, and then we'll take it up, OK? We'll do it one more time. OK, so there it is. Up again, and I'll give you 2 minutes to try it one more time. Talk to the people around you. How would you do this problem? OK, 10 seconds left. Put in what you think the limit is. OK. So I'll wait for people to stop talking, and then we'll take it up. OK, let's look. What did people think this time? Did the votes change? All right, OK, this is great. So people drifted away from minus infinity and plus infinity. Minus infinity and plus infinity are both wrong. Those are not the right answers. There is no minus infinity or plus infinity in this problem. People drifted towards does not exist. Does not exist was the most popular before by a little bit. But the correct answer is none of the above. None of the above is correct. Only 32% of people got this one right. This one is on your homework. And in fact, I would say this is one of the kind of like easier types of limit problems that could be on the midterm too. So let's go over it, because I think people aren't quite remembering how to do these ones. How do you do these ones? And this is the reason I'm doing it today, is because we're doing similar problems in our notes. You start small, and you work your way up. So you start off with something small, and you combine it together with other things to get a more complicated limit. And what is the starting small? I think it's the n to the minus 2. So let me copy this problem down and show how I would do it. OK, and I'll ask people to stop talking while we're going. I've gotten some complaints from students that people near them are talking, so it'd be nice if people were not complaining about that in the course. OK, n to infinity of, what was it, 5 minus n to the minus 2 all cubed. All cubed. And we're going to start off with this n to the minus 2. So just like a molecule is made of atoms, we're going to solve this limit by doing it one atom at a time. And the most important atom to understand is this n to the minus 2. What is n to the minus 2 doing? If we can figure out what n to the minus 2 is doing, we can combine it with the 5 and the 3, and then we'll figure out our final answer. N to the minus 2 is the same thing as 1 divided by n squared. 1 divided by n squared. What is 1 divided by n squared doing? Well, the bottom is the number n squared. As n goes to infinity, what is n squared doing? It's getting bigger and bigger and bigger. So for example, if you put in n equals 10, you get 100. N equals 100, you get 10,000. N equals 1,000, you get 1,000,000. N squared is getting bigger and bigger and bigger. And when you do 1 divided by something, it's getting smaller and smaller. So if you need to, it's OK to sort of draw a little table. When n is, let's say, 10, then n squared is 100. And 1 over n squared is 0.01. When n is 100, n squared is 10,000. And this is 0.0001, right? 2 more zeros? You should get 2 more zeros. So the moral of the story is 1 over n squared is going to 0. The limit is going to be 0. As n gets bigger and bigger, the n squareds get bigger and bigger forever. These go to infinity. And 1 over n squared goes to 0. This limit equaling 0, I just did it sort of from first principles just by thinking about it. But this was one of our limit rules. This was one of our rules, that this limit is 0. 1 over n to any power, the limit is 0. And if you know that, you know this thing over here is going to be 0. This thing is going to 0. Then you can unpackage and figure out what the whole limit is doing. So how do we do that? The first thing I'm going to unpackage is this power of 3. And by the limit rule for powers, we're going to have the limit as n goes to infinity of 5 minus n to the minus 2 all cubed. This is the limit rule for powers. Right? So the limit rule for power says if you do the limit of something cubed, you might as well do the limit first and then cube that. That's what we've done. So the limit rule for power says you can interchange the order of the limit and the cubing function. And there's also a limit rule for sums, which says that you can interchange the order of this 5 with the limit. So you can do 5 minus the limit as n goes to infinity of n to the minus 2 all cubed. And the reason is because of the limit rule for sums. Limit rule for sums. So the limit of 5 is always 5. If you're doing 5 minus something and you do the limit, you might as well do 5 minus the limit of the something. It's going to be the same. So these were all limit rules for sequences that we did, I think, 2 weeks ago. But it's worth reminding you. And last but not least, now we have the limit I just did, right? This limit that we did in green, this guy, that was 0. That was 0. So the answer is 5 minus 0 to the power 3. 5 minus 0 to the power 3, also known as 5 cubed. And if you want, that's 125. So that is the final answer, 125. And it was not infinity or minus infinity, or it does not exist or anything. It's an honest number, 125, because the limit of this stuff on the inside is going to 0. Any questions or comments about that one? This one is straight from your homework. So this is a good time to ask me before you have to do it before midnight tonight. OK. So what are we doing today are more of these things. This was the limit of a sequence. We're going to do the same exact strategy, but on limits of functions. Limits of functions with the x's and the y values. It's more complicated because you have x's and y's. We're starting today on this page, 385, I think it is. 385. So I'll let you guys find it. Rules for limits. And it really should say rules for limits of functions. Functions. OK, I'll give you a minute to flip there while I also get my copy. OK, so what are the rules for limits of functions? The first thing that is on this page is algebra of limits. These are the exact same rules as the rules for limits of sequences like we just used. There's this first one is the sum rule, the sum or difference rule, diff rule, right? The limit of the sum or the difference, you want to do the limit of f plus g, you can do the limit of f, the limit of g, and then add them together. Then there was the constant multiple rule. Constant multiple. That's the next one. Then there was the product. The limit of the product is the product of the limits. If you want to do the limit of f times g, you do the limit of f, you do the limit of g, you multiply them, that's the answer. And finally, there was the quotient. If you do the limit of f divided by g, what is the limit? It's the limit of f divided by the limit of g. There is one special thing to watch out for here, is you better make sure you don't divide by 0. If you're trying to divide by 0, the limit does not apply. The limit rule does not apply. The answer could do anything. And just like we saw before 2 weeks ago, there is an important caveat you got to make sure you don't forget about, which is that the limits must exist. I would write this in big letters over here. And the limits, this limit and that limit, must both exist. Must both exist. If they don't exist, then the limit rule does not apply, and the answer could be anything. So in those situations, when the limit rule does not apply, you got to do some manipulating with algebra before you can find the answer. So it's definitely worth it to be aware of this rule, and when it doesn't apply, that means you're going to have to do some more work first. So all of those are the same as before, as they were for sequences. Here is the verbal statement of the rules. The limit of the sum or difference is the sum of the limits, or the difference. The limit of a constant multiple is the constant times the limit of the thing. The limit of products is the product of the limits. We're changing the order that we do algebra operations with the order we do the limit, right? Sometimes you do the limit first, sometimes you do the limit second, and they are equal. I like this comment. The rules are all very handy-dandy, but before we can use them, we need to know how to deal with specific classes of functions. What this is saying is that these rules don't actually tell you what the limit of anything is, they just tell you the limit of something in terms of the individual parts. It says if you know the limit of f and you know the limit of g, you can combine them to get the limit of f plus g. So these are the rules for combinations. Rules for combinations. Rules for combinations. On the example we did as our warm-up problem today, that was like all the stuff we did on this side. All the stuff on this side of the page, this was combinations, right? Combinations. But you see, no matter how much combining you do, you eventually get to a limit like this one, the limit of n to the minus 2, and you have to be able to do that limit. So this kind of limit I call an atomic limit. That's like the atom, and then we combine them with the rules to get the limit of the full molecule. And so far, for limits of functions, the same rules apply, the same combining applies, but what are the atoms? What do we know how to do the limit of to combine to get more complicated limits? And there is a nice answer. There is a nice answer, which is polynomials. Polynomials. Limits of polynomials. So here is a rule. This tells you that polynomials are a type of atom. Polynomial. These are the atoms. We know how to do the limit of any polynomial. How do you do the limit of any polynomial? If you want to do the limit of the polynomial p of x, as x goes to a, the answer is p of a. In other words, you can just plug in x equals a. So I'll say this one more time in a different way. If you want to do the limit as x gets really, really close to, but not equal to a, this is x is close to, but not equal to a. So this whole limit idea that we spent a few classes on, x is getting closer and closer to a. It's never exactly equal to a. It's getting closer and closer. It's approaching on Desmos. That is the limit. And if you want to know what the limit is, what do? You just plug in x equals a. And those two things will be equal. This is a very nice property. This lets you find the limit. And I will say, there's a little note on the next page trying to tell you how weird this is. This may seem strange because as x goes to a, we never actually reach x equals a, right? The whole left-hand side over here, I made a big deal about this. X is not equal to a, right? So for a limit, x is not equal to a. We never actually reach x equals a. Limits do not reach x equals a. That's what this is saying. However, there's a however, in the evaluation of the limit, we do take x equals a. This is saying the left-hand side, on the left-hand side, or I guess the right-hand side, p of a, that is x is exactly equal to a, exactly. So if you go back to that equation, you plug in literally x is exactly equal to a, and that tells you the value of the limit. OK, this should be weird. You should find this extremely uncomfortable. Why is it OK that something where we never reach x equals a is given by x equals a exactly? And in fact, last class, on Friday's class, I made a big deal. I was jumping up and down and saying the value of the function does not tell you what the limit is, right? I said it doesn't matter what it is. Sometimes it's equal, sometimes it's not equal. What is going on? Why is it that on Friday I said they're not related? I said these two things, this and this, are not related, and today I'm saying they are related. What is going on? I wanted to explain this, and I came up with this analogy, and I think I mentioned the analogy last time, but now I went really hard on the analogy. Here's my little spreadsheet, my presentation of my analogy. This is like when you want your parents to buy you a cat, and you make a little like PowerPoint presentation, all the reasons you should buy a cat. This is my reasoning for what I did on Friday, where I said the two things are not related, and what I'm doing today, where I'm telling you they're equal. And my analogy, like on Friday's class, was rectangles. So we want to understand functions. Functions are hard, so I'm making an analogy to rectangles, which is something you hopefully understand. What are rectangles? Well, rectangles have two things. They have a height and a width, right? How wide are they? How high are they? Those are the only two things to specify a rectangle. And in general, what is the relationship between the height and the width? So if I am thinking of a rectangle, how are the height and width related? They're not related. There's no relationship. If I have a rectangle and I say it's 2 meters tall, how wide is the rectangle? It could be anything, right? It could be a really skinny rectangle. It could be a super long rectangle. You don't know. There's no relationship between the height and the width. And this is exactly what I said about functions on Friday. So functions have two things. The value of the function, f of a, that's exactly at x equals a. And there's the limit. That's getting really close to x equals a, but not equal to. And those two things, on Friday, I said they have no relationship. If you want to know the limit, knowing the value of the function does not help you. If you want to know the value of the function, knowing the limit does not help you. They are not related. One of them is about getting close to x equals a, and the other one is exactly equal to x equals a. They could be any combination of weird things. All right. On the other hand, there's a special type of rectangle. There's a special type of rectangle called a square. You know about squares. Squares are this beautiful type of rectangle, and for a square, there is a relationship between the height and the width. For a square, the height equals the width. So if you want to know height and width, and you know it's a square, then you have an in, right? If someone says the height of my rectangle is 2 meters, and by the way, it's a square, now all of a sudden you know the width is also 2 meters. This is just like the functions that we're talking about today. So on Friday, I said there's no relationship, but today we're talking about these special functions. They are called continuous functions. Some people call them just plug-in functions, or they're just plug-in-able. And for those functions, these special functions, the value of the function is exactly equal to the value of the limit. So in general, there's no relationship, but for these special things, just like squares, there is a relationship, and that they're just equal. So this is just like it's really convenient to find the width of a square, because if you measure its height, you automatically know its width. It's very easy to find the limit of these special functions because you just plug in the value. It's so easy. You don't have to worry about this getting close thing. You just use the fact that it's a special function that automatically tells you the limit. And what is written in the notes is basically telling you your first type of special function. The first type of special function is polynomials. These ones are just plug-inable. These are continuous. They're just plug-inable. So just plug-in is how I like to think about it. They're just plug-inable functions. So anytime you want to calculate a limit for one of these special functions, it's like finding the height of a square. You just plug in. Very simple. And we'll see some examples now. You'll see how easy it is. Exercise 182 is the first example over here. How do you find these limits? So if we were doing these on Friday's class, we would have had to draw the graph and get really close and worry about all that stuff. Worry about the left limit and the right limit. But today, we can just plug in. These are all polynomials, so we can just plug in. Just plug in. And again, this is because somebody already did the hard work and told us these are just plug-inable functions. Let's do this one first. The limit as x goes to 3 of x. Well, it's polynomial. Plug in x equals 3. You get 3. Every time you see an x, you plug in 3. Here's another one. The limit of 3x squared minus 2x plus 5. We're doing x goes to 1, so we plug in x equals 1. X equals 1. So we get 3 times 1 squared minus 2 times 1 plus 5. That is the limit. You can just plug in x equals 1 because somebody told us it's one of these special functions where you can just plug in. What's the answer? 3 minus 2 plus 5, also known as 6? 6. No. Yes, 6. Okay, good. Mental math. Good. Okay, there's one more. 7. 7 is a polynomial. There's no x's there, so it's very easy to plug in all the x's. Every time you see an x, you plug in 6, but there are no x's, so the answer here is just 7. Okay, just plugging in, very easy. So on Friday, I said it was quite hard in general to find limits. These functions, it's a breeze. It's super easy. Result 43 is giving you even more good news, that if you have a rational function, you can just plug in as long as the bottom is not 0. So can just plug in unless bottom is 0. So if the bottom is 0, you cannot just plug in. The limit laws do not apply. You got to do something else. You got to maybe simplify or something. But as long as you're not dividing by 0, it's okay to just plug in for these rational functions. These are ratios of polynomials. So if the top is a polynomial and the bottom is a polynomial, it's all okay. And there's an example of that in the notes. Here's the example. X squared plus 1 divided by x plus 2. I'm going to just plug in JPI x equals minus 1. What do you get? Minus 1 squared plus 1 divided by minus 1 plus 2. Okay, this is minus 1 squared plus 1 is 2. Minus 1 plus 2 is 1. So the answer is 2. So I just plugged in x equals minus 1. Okay, so now we have some rules. We have the simple rules like plus, minus, times, divide. We have these special functions that we can evaluate limits for. And by combining them, you can do all sorts of harder limits. In the notes, they give us a couple more rules. So this is another combining rule. Combining rule. This is the one I called the power rule before. If you have the limit of a power, it's the power of the limit. We did this one earlier today. Let me freeze this. We used this rule in our first example when we did the power 3. Right? So if you understood how the power 3 went out, that's what the rule is saying. Okay. Do they have an example in the notes? I believe they do. Here is the example. It's the exercise 184. It says, please do the limit as x goes to 2 of x squared minus x plus 4 cubed. And you can write this whole thing. This 3 becomes an exponent on the outside. And now you can do the limit as x goes to 2 of x squared minus x plus 4. And this guy in the middle, you can just plug in. So what is the answer? 2 squared minus 2 plus 4, all cubed. Okay, and you can work out what this is. 2 squared minus 2 is 2, plus 4 is 6. So this is 6 cubed. Okay. So the point is the cubed on the outside is no problem. You can pull that right through the limit. Okay, there's one more rule. It's basically an identical rule. It's the root rule. The root rule. Let's say root law. That must be why it says root law. And I have to press this button urgently. Okay. Okay. The root law. So you can do the same thing we did with the power of 3, but with a cube root or a square root. Question here first. Yes, I can put that question back. Yes. Absolutely. Yeah. There you go. Okay. So same exact thing for roots. And there are 2 examples here. I'll do one of them. Yeah, I'll do 185. That one's easy. And then we'll leave this one. You guys can try this one. Or you can do it as an extra video at home. I will post it. But the first one I will do is the limit as x goes to 8 of the cube root of x. And the cube root of x is not a polynomial. So you cannot just plug in on the cube root of x. But what you can do is pull this cube root, pull that out. So the cube root goes on the outside. And now we have a nice little guy in the middle. And that guy is just the function x. That is a polynomial. And now we can just plug in. So now we just plug in. And we get the cube root of 8. The cube root of 8. And the cube root of 8 is 2. So this one is 2. I'll leave this one as an extra video or for you to try at home. But it's also not too hard. And if I recall correctly, this one also works out to 2. Maybe I'll say what the answer is. If someone wants to try it. Yeah, it's 2. So you try doing it. You pull out the square root. You plug in. It's going to be 2. OK. These are all the rules. It's basically the same rules as for sequences, but now we have this just plug in rule as well. And by combining it, we can do all sorts of examples. Now, the thing is, the examples, by combining them in more complicated ways, can get more and more complicated. And I wanted to show you one that involves one-sided limits. So this one I will also leave as extra. But I want to talk about this one, because this is something that did not happen with sequences. So with sequences, we didn't have this left and right business. But with limits of functions, we have to worry about the left and the right-hand limits separately. So in this problem, we have a piecewise function, and it has 3 parts. There's this part when x is less than 1. There's this part when x is equal to 1 exactly. And there's this part when x is bigger than 1. And when you want to go do the limit, you have to know which part you're using. So I'm going to do this one first. When x is going to 1 from the left, when x is going to 1 from the left, you have to know that that means that x is less than 1. So x is going to 1 from the left. Remember, we had that on Desmos coming in from the left-hand side. Those were values on the number line where x is slightly less than 1. And if x is slightly less than 1, the only thing that matters is this part of the function, x squared minus 2x plus 4. So this thing is equal to the limit as x goes to 1 minus. And the point is that we can replace the function f with this nice quadratic equation, not like that, x squared minus 2x plus 4. And x squared minus 2x plus 4 is a polynomial. And because it's a polynomial, we can just plug in. Now we can just plug in. Just plug in. So I want to just take a step back and say what I did here. The original function f was not plug-inable, right? F on its own is not a polynomial. It's this crazy combination of lots of things. So f is not a just plug-inable function. We cannot just plug in into f. But I showed you that the limit of f is the same thing as the limit of x squared minus 2x plus 4 by using what I know about limits. So because of the fact that x is less than 1 here, these are equal. And now I'm ready to just plug in. So I took something complicated and I reduced it to something simple by what I knew about limits, and now I'm ready to just plug in. So now the limit will work. It's going to be 1 squared minus 2 times 1 plus 4. 1 minus 2 plus 4, also known as 2. 3, also known as 3. OK, so the limit is 3. And I sort of had to do several maneuvers to get this function down to the answer 3. This is typical in this situation. You have to combine different skills. Yeah, question up here. What was the last part of the question? OK, this is a fantastic question. So, So the question was, what x is going to 1 minus. Why did I plug in x equals 1? So maybe I'll be more specific. I said just plug in, and I plugged in x equals 1. But why did I plug in x equals 1 and not something else? So this is going back to the definition of what this x goes to 1 minus means. And I think it's helpful to draw the number line. So in the number line, we had x equals 1 exactly here. And x goes to 1 minus meant a very specific thing. It meant a sequence of x values, which is going to 1. So the limit of the x values is exactly 1. But they are coming in from the left side. So we're specifying the direction, but the final location is still x equals 1. So this thing specifies the direction is like this, kind of coming in from the left-hand side. But the final value is x equals 1. And if you want, like this limit is the same thing as the limit as x goes to 1 with no direction specified. They are both the idea of getting very, very close to x equals 1 from either side. The limit is going to be just plug in x equals 1 no matter what you do, because it's the nice polynomial where you can just plug in. So another way to say it, and maybe this is like the technical definition, this limit exists and is just plug in. And if the two-sided limit exists, then both the left and the right limit are both equal to that. So if you want, you can do it that way. But I think more fundamentally, the final destination is x equals 1. This minus sign just specifies the direction. it's not a surprise that you're still plugging in x equals 1. Yeah, great question. Any other questions or comments about that one? Okay, let's do the other side, which is the limit from the right. The limit from the right. This is the limit as x goes to 1 plus. This is x bigger than 1. And what this means is we're still going towards x equals 1, but from the other side. Okay? And when you do that, the important thing to realize is that the only part of the function that matters is that 8x to the 4 minus x squared minus x minus 3. And that's because that is what f is if x is bigger than 1. So from the point of view of the limit only sees that formula. The limit only sees that formula. So this limit is the limit as x goes to 1 plus, and it's 8x to the 4 minus x squared minus x minus 3. And so, that is an important step because x is bigger than 1. Because x is bigger than 1, I can replace f with that nice formula. And now I can just plug in. So just same exact reasoning as before. I can just plug in x equals 1 to get 8 times 1 to the 4 minus 1 squared minus 1 minus 3. 8 minus 1 minus 1 minus 3, that is 3. 3. Any questions about either the left limit or the right limit? So you see, when you compute them, you have to use two different branches of the function, right? The left limit used this guy up here, and the right limit used this guy down here, because those were the two parts of the function. The next part of the question says, please find the limit. Please find the limit. Okay? And what is the limit? It's very tempting to think, okay, in the first part of the question, we used one part of the function. In the second part of the question, we used the second part of the question. You might think, based on the pattern, you should use the middle part of the function. But you should not. We do not use the middle part of the function. The limit equals 3 because the left and right limits are equal. The left and right limits equal 3. So if the left limit and the right limit are equal, no matter what they're equal to, that is the value of the two-sided limit. This value that was over here, when x equals 1, the value 5 is totally irrelevant. This is irrelevant. Irrelevant. So it's very important to keep your eye on what's going on here. The other two formulas mattered a lot, but the x equals 5, or the y equals 5 there, that does not matter. This is irrelevant. Okay, so that's an example of combining everything we know about limits with the limit rules we just learned to do some more complicated limits. Are there any questions or comments about that one? Okay, I'm going to set you guys loose on another one, and that is this one on the next page, the limit as x goes to 0 of x divided by x. And I'm going to have you work on it for 2 minutes, and then I'll put up some multiple choice answers after 2 minutes for you to try, okay? So try working on it, and then I will give you a chance to multiple choice answer. Okay, I'm going to pause the clock here with 30 seconds left, and I'm going to give you some options, and you should select the best option given what you've done. already. So this is only exercise 2. So you have a bunch of different multiple choice options. What could this limit be? And I want you to choose, based on what you've done so far, what you have. Okay, 10 seconds left, so put in a guess if you're not sure. Put in whatever you think looks most right. Okay, let's take a look at the answers people gave. What answers did people choose? All right, so 77 people answered. 22 people chose 1. 1 was popular. 3 people chose 0 over 0. So I think I mentioned a few classes ago that 0 over 0 is never the answer to a limit. 0 over 0 is not a number. I think most people got that message. So 0 over 0 is definitely not right. A lot of people said does not exist. So let's take a look at this one and see what is right. So the first thing to notice is that the top is the function x, and the bottom is the function x. And so it's true that the limit of the top, as x goes to 0, the limit of the top is 0, and the limit of the bottom is also 0. So in some sense, it's type 0 over 0. This is a type 0 over 0 problem. So this is type 0 over 0, because the top is going to 0 and the bottom is going to 0 if you look at it in the sort of obvious way. And 0 over 0, it doesn't mean the answer is 0 over 0. 0 over 0 is not an answer. It is type 0 over 0. It means we can't apply our rules. Our rules do not directly apply. Our rules do not directly apply. So I think most people are tuned into that, which is great. Directly apply. So the rules only work if it's not a 0 over 0. Some people call this an indeterminate form. Indeterminate means our rules don't apply, we got to do something else. Our rules do not determine the answer. It looks like a lot of people said that it does not exist. It does not exist. So a lot of people are thinking, if the rules don't apply, therefore the limit does not exist. If the rules don't apply, therefore the limit does not exist. And that is incorrect. So the correct answer here is 1. If you chose does not exist, it means you have an incorrect understanding of what happens when the rules don't apply. When the rules don't apply, that doesn't mean the limit does not exist. It means you got to think about it a different way. You got to do some algebra to get to the right answer. You have to try something else. So it's a little bit like, I don't know, you're playing like World of Warcraft and you find an enemy that's immune to fire. If you're using fireballs on them, it's not working. That doesn't mean the enemy is immortal and will never be killed. It means you need to get your ice bolt out. I don't know. You got to try something else. You need a different weapon in your toolbox. Okay? And in this case, the limit is going to be 1. Why is the limit going to be 1? I'm going to use the weapon of simplifying the top and the bottom. So I'm going to do this, which is x over x is equal to 1 if x is not equal to 0. This is the key result that you need to do this problem. I call this the key simplification. Simplification. X over x equals 1 if x is not equal to 0. You might remember this. This kind of question was on the high school algebra quiz. And it's just saying that you can cancel out an x from the top and the bottom as long as x is not equal to 0. If you understand this algebra result, then we can use it to do the limit as x goes to 0 of x over x. X over x is equal to 1 except when x equals 0. And limits never care about what happens exactly at x equals 0. So x over x I can replace with 1. Okay, so I've used the key result to replace x over x with 1. Now I got to do the limit of 1. 1 is a polynomial, so I can just plug in if you want, or however you want to do it. Okay, it's not 0. Hold on. I got excited. Okay, just plug in. You just plug in x equals 0. And there are no x's, so it's just 1. And that is why the answer is 1. We simplified it. That was the key tool we used. Yeah? No. It turns out that this kind of thing happens all the time. And maybe I'll give you a little preview ahead to where we're going in this course. You might think this is some sort of like technicality. Okay, x over x, it's like silly. Like you put the same thing on the top and the bottom. We are going towards doing something called derivatives. And derivatives are about velocity and things like that. And when you do velocity, there is an issue of finding the velocity of a car, because to figure out how far a car is going, you need to wait some amount of time. And if you want the instantaneous velocity, like how fast it's going right now, you have to divide how far it went divided by how much time you waited. And if you want the instantaneous velocity, those are both 0. Like if I show you a picture of a car, and I say how far did the car move in the picture, it's 0. Well, how long was the car moving in the picture? Also 0. So this kind of 0 divided by 0 with an x in the top and the bottom is actually the most important example to understand. It's exactly what gives the velocity of a car, where the top is going to be how far the car went, and the bottom is going to be how long you waited for. So we're going to see that in chapter 11. Yeah. It's not true that it's always equal to 1. This is a good point. Yeah, maybe I should. This is not a great example because it has this coincidence. Maybe it's worth saying, note. 0 divided by 0 is not always 1. Not always 1. And again, I think you should only ever say 0 over 0 in the context of type 0 over 0. So let me add that word in. Type 0 over 0. This was a type 0 over 0. They're not always 1. And in fact, exercise 190, which I'm going to have you guys try quickly, this is another type 0 over 0, but the answer is not 1. This one is also type 0 over 0, but the answer is not 1. When you have a 0 over 0, it means you got to do some work. You got to use some simplifications or something to find the answer. So I'm going to give you guys 2 minutes to try exercise 190, and then we'll take it up. Any questions or comments before we start? Okay, so go do exercise 190. Think of what kind of simplification you could do for that one. Okay, I just opened it up to accept answers. This time the answer is a number. Or remember, you can use does not exist DNE or /inft. If you think it's infinity or minus infinity, you can do that. Or if you think it does not exist, you can do that. Okay, let's take a look at what people said. What do people think this limit is? Okay, so 1. 1 is not correct this time. I said it's not 1. I wasn't kidding. It's not 1. Okay, 5 was popular. 25 people in 5. Infinity, 7 people. Does not exist, 9 people. Otherwise, people were all spread out. And the most common answer here, 5, is the correct answer. So if you got 5, really well done. I think you're understanding what's going on. Just like the previous problem, the key to this one is to do some simplification. So you can't directly plug in. It's type 0 over 0. We got to do some simplifying. And in this case, the simplifying you got to do is by factoring x squared plus x minus 6. This is x squared plus x minus 6 is the same thing as x minus 2 times x plus 3. So this part so far, I haven't done anything except I've factored. Factoring is something you should be able to do. The next part is the type of simplifying we did on the high school algebra quiz. X minus 2 times x plus 3 divided by x minus 2 is the same thing as x plus 3 for x not equal to minus 2. So this is the equivalent of what we did before. This is the key simplification. The key simplification. And the point is that x minus 2 can cancel from the top and the bottom as long as x is not equal to 2. And x is not equal to 2 is fine because x is not 2 here. X is getting close to 2, but not equal to 2. And so by the key simplification, the limit that we're looking for, the limit as x goes to 2 of x squared plus x minus 6 divided by x minus 2 is exactly the same as the limit of x goes to 2 of x plus 3. This is by the simplification. By the simplification. Okay, so we're left with the limit of x plus 3. How do you do the limit of x plus 3? You just plug in. Just plug in. Okay, and that completes the whole shebang. 2 plus 3 equals 5. So if you got 5, well done. That's how you do it. Okay, we'll see you guys on Wednesday.